Hello class, welcome back. In 7.4 we are going to look at the mole, and that's when we are starting to deal with the chemical quantities. Okay, so not just reactions, now we are going to start to look at moles. So our learning goal is to use Avogadro's number. We will define what that number is to determine the number of particles in a given number of moles. And so number of moles is a chemical quantity, and we are going to associate it with Avogadro's number. Accounting terms states a specific number of items, right? We have 24 cans, we have 144 pencils, 500 sheets or one ream, 12 eggs means 1 dozen, 24 cans is 1 case. So the term dozen, case, gross, and ream are used to count the number of items that are present in that unit. As if this is an entire unit, this is 1 case, it's 1 unit, but within that unit there are 24 cans. So we will relate to that in explaining Avogadro's number. Avogadro's number is the following. So small particles such as atoms, molecules, and ions are counted using the mole. So that's what we count them. That's the unit, or that's the quantity that we use to count atoms, molecules, and ions. A unit that is called Avogadro's number. Each mole, 1 mole, contains 6.02 times 10 to the 23rd items. Okay, so it shows us that 1 mole contains 6.02 times 10 to the 23 items. Avogadro's number is this long number, it's this very large number. In each mole, there's this much atoms, molecules, or ions. So it is named after Avogadro, who's an Italian physicist who came up with this idea. So 1 mole of an element equals 6.02 times 10 to the power 23 atoms of that element. 1 mole of carbon has 6.02 times 10 to the 23 atoms of carbon. So that unit is like as if 1 case of carbon has this much atoms of carbon. 1 mole of carbon has this much atoms of carbon, right? So 1 mole of sodium has this much atoms of sodium. 1 mole of sulfur contains 6.02 times 10 to the power. So it's a standard quantity that we use for all different elements. So 1 mole contains the same number of atoms for all elements. What we're going to learn now is how to convert particles to moles. So 1 mole of aluminum has this much, 6.02 times 10 to the 23rd atoms of aluminum. Sulfide, water, vitamin C, NaCl, it's the same. It's not just for the element, it could be for a molecule. So 1 mole of water has 6.02 times 10 to the 23 molecules of water. Okay, here 1 mole of NaCl has 6.02 times 10 to the 23 formula units of NaCl. So it's a case that has NaCl. The total number of these NaCl is 6.02 times 10 to the 23. So Avogadro's number can be written as an equality and 2 conversion factors. So 1 mole is equal to this much particles. So we can convert from mole to particles or particles to mole, right? So this is an equality. We can write 2 conversion factors from it. 1 mole over 6.02 times 10 to the power 23 particles, and 6.02 times 10 to the power 23 over 1 mole. Those are the 2 conversion factors. So our guide to calculating atoms or molecules is by using these conversion factors and using that equality statement and the conversion factors. So we state the given and the needed as always. We write a plan to convert moles to atoms or molecules, and then we use Avogadro's number to write the conversion factor, and we set up our problem and calculate the number of particles. So here's an example. Avogadro's number is used to convert moles of a substance to particles, right? How many carbon dioxide molecules are in 0.500 moles of CO2? So we know that we have 0.500 moles of CO2. How do we calculate how many particles or how many molecules are there? This is how we do it. So the first thing, we state our given. We are given that we have 0.500 moles of carbon dioxide. What we need is the molecules in that quantity. So we need to convert from moles to molecules using Avogadro's number. That's the only way. So what is the equality statement? It is 1 mole equals to 6.02 times 10 to the power 23 molecules of carbon dioxide. We write our first conversion factor and then our second conversion factor, and then we set up our problem. So initially we are given moles, so we need to write the conversion factor that has moles in the denominator, so it will cancel. And therefore we would be given 3.01 times 10 to the power 23 molecules of carbon dioxide, which is exactly half of that, because 1 mole has this much, so half of 1 mole should have half of this number of molecules. The sample question another sample question involving Avogadro's number is, the number of atoms in 2.0 moles of aluminum is what? So again, how do we do that? We analyze our problem. We are given the number of moles. We are asked to find the number of atoms. So how do we do that? We go and we write our plan, which we are converting moles to atoms using Avogadro's number again. We can convert moles to molecules, moles to atoms, moles to ions. Okay, so so 1 mole is equal to 6.02 times 10 to the power 23 atoms of aluminum. We write our two conversion factors, and then what we do is we set up our equation. We have 2.0 moles of aluminum times this conversion factor, because that one has moles on the denominator, so it would cancel. Therefore, it would be 2 times that, which would be 1.2 times 10 to the power 24 atoms of aluminum. So the correct answer would be C, guys, okay? Here's another sample question. The number of moles of sulfur in 1.8 times 10 to the power 24 atoms of sulfur is the following. 1 mole of sulfur atoms, or 3 moles of sulfur atoms, or 1.1 times 10 to the power 48 moles of sulfur atoms. So we have the number of atoms, and now we need to get the number of moles. So we will use another conversion factor, right? So we need to, we are given the number of atoms, we need to calculate moles, so we need to convert atoms to moles using Avogadro's number and using our our equivalency statement, which has two conversion factors, one of which we are going to use. We are given atoms, so we will have atoms in then our denominator, and so that will cancel. 1.8 times 10 to the power 24 multiplied by 1 divided by 6.02 times 10 to the power 23 gives us 3 moles of sulfur, and the correct answer, guys, is B. So these are typical examples where you will use moles and how you will convert between moles and particles, moles and atoms, moles and molecules, moles and ions. So the chemical formula here, we're taking an example in a formula. So there's aspirin. This is the formula of aspirin. So the number of atoms in 1 molecule of aspirin, there are 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9 carbons. How many hydrogens? 8 hydrogens. How many oxygens? 4 hydrogen atoms in 1 molecule, right? So here are the atoms in 1 molecule. In this 1 molecule, we have 9 carbons, we have 8 hydrogens, and we have 4 oxygens. So moles of each element in 1 mole. Now we have in that 1 mole of molecule, we have 9 moles of carbon, which is the fraction, 8 moles of hydrogen, and 4 moles of oxygen. And let's see what that means. So here we have, sorry, this arrow should be on the 9. That would be, this is 1 molecule. It has 9 atoms of carbon, 8 atoms of hydrogen, and 4 atoms of oxygen. The moles of each element in 1 mole of compound. There are 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen in that 1 compound. This is what it translates to, okay? In 1 mole of that compound. So the subscripts are used to write conversion factor moles of each element in 1 mole of compound. Let's see why we do that, and why are we interested in writing and saying that in 1 mole of compound we have 9 moles of carbon, we have 8 moles of hydrogen, and 4 moles of oxygen. Why do we say that? It's because we need to write conversion factors. So for 1 mole of aspirin, the possible conversion factors are this: 9 moles of carbon in 1 mole of this, 8 moles of hydrogen in 1 mole of aspirin, 4 moles of oxygen in 1 mole of aspirin. And again, this would be flipped, this would be flipped, and this would be flipped, and we use these in calculations. So when we are calculating moles of an element in a compound, when we are asked, for example, in this compound, how many moles of carbon do you have? How do we know? The way to do it is we use these conversion factors. We need to know that there are the number of moles is equal to the number of atoms of that compound, of that element in that compound, and we write down our conversion factors. So we state the needed and the given quantities, the plan, and then write the equalities and conversion factors and set up the problem. So how many atoms of oxygen are in 0.15 mole of aspirin, this much? This is the formula of aspirin. So atoms. So what are we needing? What are we given? We are given that we have 0.15 mole. Sorry, this is 0.15. Let me just check something real quick. Yes, it is 0.15. So please, can you correct this? This is not 1.5. This is 0.150 of aspirin. We are asked to get the number of atoms of oxygen in this molecule. Okay, so let's see. In this much mole of aspirin, or in this molecule, in this one compound, we know that we have 4 oxygen or 4 moles of oxygen. But in this much, 0.15 mole of aspirin, how many oxygen atoms are there? So what do we need to do? We need to convert, first of all, the moles of aspirin to moles of oxygen, and then the moles of oxygen, using Avogadro's number, we convert them to atoms of oxygen. So how many atoms are there? The first thing that we do is write the inequalities that we need, and we will need to do it in 2 steps in this case, because we are doing 2 steps, converting from moles to to moles of oxygen, then from moles of oxygen to atoms of oxygen. So 1 mole of this much has how many moles of oxygen? 4 moles of oxygen from the subscript right here. Okay, so we write down our 2 conversion factors. Then we have 1 mole of oxygen has how many atoms of oxygen? 6.02 times 10 to the power 23 atoms of oxygen. We have 2 conversion factors. We set up our problem, guys. We have 0.15 mole of aspirin. Okay, so we have 0.15 mole of aspirin. And what do we need at the end? We need atoms of oxygen. So we multiply it first to convert it into moles of oxygen by 4 moles of oxygen over 1 mole of aspirin. Therefore, mole and mole of aspirin will cancel out. And then after the moles, we need to multiply by another conversion factor, which gives us atoms. Therefore, it would be 3.61 times 10 to the power 23 atoms of oxygen. This is the end of this slide. I will see you in the next one. There's, I would say, probably 6 more, but I'm dividing them into short videos so that you will pay more attention and you won't get bored after watching a 30-minute video. Thank you. I will see you in the next one, which will be 7E. Thank you.